Welcome to the continuation of my video on worked example of simple linear regression analysis. So this is part 2 of the video. If you have not watched part 1, I encourage you to go back and look at part 1 because you need to follow what we did there to be able to understand this second part of the video. Again, my name is Shedrack Akindele of the Federal University of Technology, Akure. In this video, we'll be doing some tests of the equation we obtained in our previous video. So let's get into it right away. So we want to look at some simple criteria that we use to test regression equation. These criteria are used to ascertain how good our regression equation is. You remember in the first video, we came up with a regression equation. We want to test that equation. How good is it? Is it really something we can rely on? Is it useful? Or should we discard it and think of something else? So there are some criteria we use. And these are just simple, the simple ones here. There are much more than this, but these are the ones I'm presenting in this video. First one is test of significance of regression equation, which is the F test. And the regression must be significant for the equation to be good. Second one is coefficient of determination. We call that R squared. R squared must be high. That's the requirement. And then the final one is the overall standard error, the standard error of estimate. It is also called root mean square error. And usually we expect that the error will be low. So these are the 3 simple criteria I want to take us through in this video. So we go to the first one, test of significance of the regression equation. To do this, we will calculate the regression sum of squares, the total sum of squares, and the error sum of squares. That is SS regression, SS total, and SS error. We need to calculate those. And then prepare an ANOVA table to enable us do the F test. So let's see how we do that. First, SS regression. The formula is right there on your screen. B1 squared times sigma x squared minus sigma x into bracket square all over n. So that's the formula. And if you recall in video 1, I showed you how we obtained all these values. So it is the values we obtain from that we have brought here. And this is exactly what it is. So this is B1 squared times the entity in this bracket. This is it. You go back to the previous video, you'll see how we came across, how we came about this value. So when you evaluate that, that's multiply that out, it gives you 3093.42. So we move on to SS total. SS total, the formula is right there, sigma y squared minus sigma y into bracket squared all over n. And again, the values, these values you are seeing here, they are from the first video. And when you do the evaluation of this, it gives you 3244.76. Now we move to the last one, which is SS error. And SS error is simply SS total minus SS regression. And then you check out the values there. 3244.76 minus 3093.42. And that gives us 151.34. So that's our answer for SS error. So from there, the next thing to do is to prepare the ANOVA table, analysis of variance table, and then we'll test for the significance of the regression equation. Now, before we compute the ANOVA table, we need to specify the hypothesis we want to test. And so in regression analysis, the null hypothesis is usually that the regression is not significant. And the alternative hypothesis is that regression is significant. So let's see the ANOVA table now and look at what it is. So we have our source of variation, we have degrees of freedom, sum of squares, mean squares, F calculated, and F tabulated at 0.05 level of significance. So let's see how we compute the degrees of freedom. For regression, P minus 1. That's how you compute the degrees of freedom for regression. What is P? P here stands for number of parameters. Don't forget, in our equation, which is y equals BO plus B1x, I told you that we have two parameters, BO and B1. Those are the parameters. So P minus 1 here will be 2 minus 1, and that gives us 1. Now, the next one you look at is your your error. Degree of freedom for error is usually n minus p. N is the number of observations, which is 20 in our own case, and p, number of parameters, that's 2. So that gives us 18. And for total, it's the degree of freedom is n minus 1. N is total number of observations, which is 20, and 20 minus 1 gives us 19. Incidentally, if you subtract 1 from 19, it will give you 18, which shows that we are correct, we are in order. Now, the values you obtain from previous calculations of sum of squares, you insert them here. And then you move on to the column for mean squares. So to get each value for mean square, you will divide your SS by its degree of freedom. So for regression, it will be 3093.42 divided by 1. That's what gives us this. For error, it will be sum of squares for error divided by the degrees of freedom for error, and that gives us 8.41. Now, we don't compute mean squares for total because mean squares are not additive. So we don't say 3244.76 divided by 19. No, we don't do that. Because if you do that and you put a value here and you had these two values, they won't give you that answer here. So this space is usually left blank. We don't compute mean squares for total. Now the next is your F calculated. And F calculated is simply mean squares for regression divided by mean square for error. And that gives us 367.83. So this is our F calculated, the variance ratio. We also call it variance ratio. And the critical value, which is called F tabulated at 0.05, you obtain this value from the statistical table using the degrees of freedom for regression and error. That's 18 under 1. That will give you 4.41. 4.41. So that's the F tabulated. So what we have to do is to compare our F calculated with our F tabulated. And since the F calculated is greater than the F tabulated, we do not accept the null hypothesis. So we don't accept null hypothesis here because F calculated is greater than F tabulated. We therefore conclude that the regression is significant. That is, we accept the alternative hypothesis. So that's our conclusion. So that regression equation we developed in video 1, we have tested it now and we realize that it is significant. And that's one of the requirements. So it means we are good to go. That equation, it has met that requirement. It is good. So we move on to the next, which is the coefficient of determination. The coefficient of determination indicates the proportion of variation in the dependent variable that is accounted for or explained by the independent variable. And usually the higher the value of the coefficient of determination, the better. In other words, if you are comparing two equations, the one with higher R square would be preferred. So the formula for R square is as shown on the screen. R square is SS regression all over SS total. So from our ANOVA table, we already have the SS for regression and total. Just put them the way I have indicated on the screen, and you evaluate that formula. It will give you 0.9534. 0.9534. So that's our answer for R square. And of course, if you are to convert this to percentage, this will be equal to 95.34, 95.34%. So this result shows that 95.34% of the variation in height, don't forget height is our dependent variable, is explained by diameter, which is our independent variable. And you can see that the value of R square is high. I mean, 95%, that's quite high. So that's the result of our coefficient of determination. Next is our standard error of estimate, SEE, standard error of estimate. Standard error of estimate is also called the root mean square error, or RMSE. That's another term for it, because it is simply the square root of the error mean square. So from our ANOVA table, you remember we have mean square for error. So if we just take the square root of that, it will give us the RMSE. So RMSE describes the variation of the observations around the regression line. The smaller the value, of course, the smaller the value, that means the smaller the error, the better the regression equation. And you can see the formula there. RMSE is simply square root of mean square error, MSE. And you evaluate that, it gives us 2.9275. 2.9275. So that is the result of our our standard error of estimate. So let's now use our equation. Having tested the equation, we found out the equation is good because the regression is significant, the R square is high, error is low. Fine. Let's now use the equation to estimate the dependent variable, especially if we are given the value of independent variable. So let's see how that is done. Now remember, let's recall the equation from video 1. This is our equation. Our y is the height, x is the diameter. So we can use this equation to estimate the value of y for any given value of x. So let's say, for example, what is the height of a tree whose diameter is 30.5 cm? All we need to do is just bring this 30.cm into that formula, because that's our x, and then evaluate the formula. And that's what I've done right here, as you can see on the screen. Y equals 5.1533 plus 0.5462x. That's the formula. So given that x is 30.5, you just put 30.5 there, and you evaluate that. It will give you 21.8124. So the height, when the diameter is 30.5 cm, is 21.8 meters. So that's our final answer. So you can see how useful regression is now. So even though if you look at our raw data, we didn't measure there was no data of any tree with 30.5. But our equation now has helped us to get the height of a tree that has a diameter of 30.5. So that's the importance and the usefulness of regression equation. We can use it to estimate the value of x. Once we have solved the equation, we can always determine our y at any given value of x. So that's the end of that. Check out my other videos on my YouTube channel to learn more about different aspects of statistical analysis, as well as forest measurements and research writing, different stuff. They are available on my YouTube channel. Just check it out. And don't forget to like, share, and subscribe to my channel. Also, click the notification button in order to receive an alert whenever I upload a new video. I'll just leave you with a little advert of a new textbook I have written on statistical analysis, which is very, very important. I tell you, you don't want to miss it. Check it out.